Hello and welcome to the world of NDE 4.0. My name is Johannes Vlahne, and today is a great day because today we will continue exploring one of the hottest topics of NDE 4.0. We will continue our journey to the world of artificial intelligence, machine learning, deep learning, and neural networks. Now, in my first video on artificial intelligence, and I will leave a link to that video right here, I tried to give you a bit of an introduction. And for that, I used the most basic neural network, the so-called fully connected neural network or multi-layer perceptron. And with showing you that, I tried to take some of the fear which could be connected to AI to take that from you. Now, this time, let's discuss the neural networks with a lot of use cases in NDE. Now, but before I get started, I have to ask you a small favor. I guess you know that YouTube uses artificial intelligence to evaluate a channel. And the evaluation depends on the user interaction. The more interaction, the higher the rating. Therefore, please subscribe to this channel. Click on that little bell. Give a thumbs up to every video. Write lots of comments and watch the video all the way to the end. Especially the last two, the comments and the watch time. Those are the two most important ones. And this is how you can support this channel, how you can support my work, and this is how you can also bring NDT and NDE to the world. And now, let's get started. Now, main use of artificial intelligence in NDE. Now, the main task we have, or the most challenging task we have to do in NDE is we have to see, are there indications in the component? And if there are any indications in the component, to find them, to classify them, and to determine their size. And what you can see here, this is actually the result of an ultrasonic inspection of a large rotor forging. Or to be more exact, it's the result of a SAFT, a synthetic aperture focusing technique, ultrasonic inspection of a large rotor forging. Now, I have already done a video about SAFT, and I will leave a link to that video right here. Now, what we need to do with this image, we need to extract the features we see here. And feature number one is, that's actually the bore of the component. So that's what's supposed to be in that part. And then we have here 1, 2, 3. Those are actually two indications. And then there is a tiny one right next to that bore. So what we have to do a segmentation. We have to segment the features we need to have a more detailed look into. Next step, now we have to classify. And speaking with in terms of ultrasonics, this would mean is that a group indication or a single indication or something similar. And then finally, we have to determine its size. So we could measure its length, or with ultrasonics, most likely we would more do a sizing based on the reflected amplitude. And there is actually a possibility also to do that with SAFT. And I have done a video about that, and you can find the link to this so-called QSAFT right here. Now, size determination. This is again a feature extraction. So in essence, what we need to do is we need to do a feature extraction, we need to do a classification, segmentation, we need to do a classification, and we need to do another feature extraction. Those are the things we need to do. And those are the things we can give to an artificial intelligence. And now let's see which neural networks can do those jobs. So the first one, this is the one we looked at in the first video already in detail. And we did it on a very small, a little example, where we had an input layer with 5 neurons, 2 hidden layers with about 6 neurons each, and an output layer with 3 neurons. So in total, we have 84 connections, which means that we have 84 weights. And we have 15 receiving neurons, so we have 15 bias values. Those 99 values have to be trained. Those are the unknowns of this of this mathematical equation. And those unknowns need to be trained. For the training, what we do is, actually, we need thousands of input files. And for each input file, we need to know what the output is about. And that's how we determine those 99 values. Now, that's a little example. Now, let's talk about something which is more reasonable, like a small image, like this image with 320 times 240 pixels. Now here we would need an input layer of about 70,000 neurons. So let's say we need hidden layers with around 100,000, and let's say we want to distinguish between 10 different things, between perhaps 10 different classes of indications, or whether it's a human, a parrot, whatever, then we need 10 output layers. So in that case, we have 17,618 times 10 to the power of 6 connections. And for each of those connections, we need a weight. And for all the receiving neurons, we need a bias. Now, all those weights and all those biases, we have to train. And we have to store them somewhere once we have trained them. And storing that model takes 50 gigabytes of RAM. Just for such a still quite small example. Now, if we go to something larger, like a 2 megapixel image, and you see here in the background of this slide, you see this image, which is behind all the boxes, that's about a 2 megapixel image. And if we then do, let's say, we need an input layer of 2 million, 2 hidden layers with, let's say, 5 million neurons each, and an output layer with about 1,000 neurons, then we get up to 35 10 to the power of 12 weights. And if we want to store that model once we have trained it, if we can train it, because you can imagine for this number of weights, you also need a lot of training data. Once we were capable of training that, then we end up with a model that takes about 95 petabyte of RAM. Yeah. So I guess what you can see is those fully connected networks, they have a few benefits. They are structure agnostic, so no special assumptions are needed to be made about the input. They are broadly applicable, but they have quite a weak performance, what we have seen in the last 2 slides. But they are great classifiers. They're really great in distinguishing between, is this indication type A, B, or C? So what else can we use? And that's coming back to the so-called convolutional neural networks, CNNs. And those, what we will see, they are great in extracting features. So, now, how does a convolutional neural network work? How does a convolution work? And convolution is something which is really going back, since the beginning of image processing with computers. People were using convolutions to do that image processing. And the example which I'm showing you here, so we use that image and we use a so-called convolution kernel. And the convolution kernel we see here, that's the one for edge detection. If we apply it on that image, then that's the result we get. And you can see how powerful that is. Now, how does a convolution work? Now, an image, for a computer, an image is not an image. For a computer, an image is an array of numbers. Actually, it's 3 numbers for each pixels, red, green, and blue, but let's keep it simple and let's say there is 1 number for each pixel. So that's our image. Now, if we want to calculate the convolution for this particular resulting pixel, and what we do is we take a 5 times 5 matrix around that pixel, so a 5 times 5 around the number 33, And then we multiply 19 times 0, 61 times 0, and so on and so on. And then we add up all of them. So this is what we do. When we calculate that, it comes down to this. And finally, we can calculate that this is the number 116. Now we can calculate that for every single pixel except for a small edge of 2 pixels. Because we always need this 5 times 5 matrix to calculate the element in the middle. That's why we cannot calculate the edge. Now, you don't have to use a 5 times 5 convolution kernel. You can also use a 3 times 3 or a 7 times 7 convolutional kernel. It's just this one which I picked for this example. And finally, this is how this result, this edge detection, is calculated. Now, edge detection isn't the only one. We can do a lot more. We can sharpen our image. And now, compare those two matrices. In the edge detection, we had a negative number in the middle and one surrounding it. On the sharpen, we have a positive number in the center and negative numbers surrounding it. And what we get is an apparently sharper image. We can also do a blur. We can go fancy and do a Gaussian blur. Or we can do something like embossing. So now, I guess you can see why convolution has been used in image processing for decades by now. So why not use this technology within a neural network? And this is exactly the core of the convolutional neural networks. But instead of actually pre-producing a convolutional kernel, like an edge detection or something like that, let's train it. Let's train the 5 by 5 or 3 by 3 matrix. Now what we get once we apply this convolutional kernel is we get a so-called feature map. We do a feature extraction with it. Now perhaps we want to do multiple feature extractions at the same time. So what we can do is we can just use multiple convolution kernels. And each convolution kernel is small. It's tiny. It doesn't, to store it in our RAM or on our computer, it's nearly no memory. So we can do 16 at once, and it's no problem storing them. And at the same time, we also get a lot of features extracted out of it. Now there is one more step we need for a convolutional neural network. And it's a quite simple one. That's the so-called max pooling. So what we do is if we look here at those 4 elements, 57, 13, 55, and 72, we just keep the maximum, which is 72. We look at the next 4, we keep the 55, so we always keep the maximum. And so this is how we determine this result. So what happens to our image? Our image gets shrunken in size, but what we do is we keep the important information. We keep the information with a high amplitude. So, how does a convolutional neural network work? Because it's not just one convolution and one max pooling. No. We start with a convolution. We continue with a max pooling. We add another convolution. We add another max pooling. And perhaps we do several more of them. And then what we do is we train all those convolutional kernels. And that is what we have to save to finally apply that neural network to something else. Now, what we can do with that is we extract features. But finally, in a lot of cases, we want to come to a conclusion. We want to classify our result. So what we do is on the result of the end of our convolutional neural network, we add a fully connected network. But now that network can work on a lot smaller images. So it's not getting that big anymore. So we talked about it. Convolutional neural networks, they are good for feature extraction. They are great for processing images. They are great for data with spatial structure like audio or video files or ultrasonics or eddy current. They're also good for natural language processing. Perhaps you have used DeepL already for translation purposes. If you haven't, do it. I have actually uploaded a complete paper to DeepL. Yeah, and that German paper was translated to English, and that English translation was really good. Now, a few things to mention. Those convolutional neural networks. You always work locally with your convolution kernel. So therefore, it is translational invariant. Information which was up here stays up here. Usually you combine it with a fully connected network because you want to have a classification afterwards, but they lack global understanding. You only work locally, so you don't get a global understanding. So now we already have 2 out of the 3 things we need for NDE defect classification. Now the third one, that's image segmentation. And that's what we can do with a so-called unit. So let's see what's a unit about. Now a unit, in the beginning, it's just a convolutional neural network. So you do a convolution, you do a max pooling, you do a convolution, you do a max pooling, and so on and so on. But now comes something different, which is a so-called upconvolution. Now, if you look into the process of a convolution, you can write that as a matrix operation. And that matrix operation, you can actually inverse. Now, I will not get into the mathematical details of that, but you can just think of it kind of the inverse operation of a convolution. Now, we have now done all this feature extraction, but perhaps we want to have more information from the original image to do a segmentation. And this is actually why we copy over the stuff we had before. And then we continue working on that information. Do another convolution, do another upconvolution, again copying over. Another convolution, another upconvolution, another copying over. And finally, we are getting towards our final segmented image. And you can use that for 2D and 3D volumetric segmentation. You can use it for a lot of things where in our industry, in NDE and NDT. And if you look around, there are a lot of papers describing how powerful those units can be for NDE, and actually also for medical. So now we have the 3 things we need. We can extract the features, we can segment our images, we can classify them. Now there is a new technology on the AI horizon, which all of you will have heard about. And those are the so-called transformers. Now, the most famous example currently is ChatGPT. ChatGPT is a transformer. And there are other ones like BERT or various other ones. They are really good in terms of scalability. They model long-range dependencies. They process the entire input at once. Think about, you upload an essay into GPT and tell it, okay, please summarize it. And it will do it. And that's only possible if you can model that long-range dependency of the complete essay. It can process the entire input at once. It can consider the word position, and actually it can be integrated into convolutional neural networks. Now, the purpose for NDE, that's a different story of those transformers at its current state. Now, you can use them for a little bit, or you will be able to use them for computer vision too. So they will have a great benefit also for NDE defect recognition. But already right now, we can use those transformers for text writing tasks. If you have to write something, you can use GPT. Now, I will not talk more about those transformer technologies now, but in a future video, I will go into not the details, but I will try to explain you, okay, how do those transformer models, how do they work, and how can you take the best out of it? So, thank you for watching. If you have any comments, if you have any questions, feel free to leave them down here in the comment section. Next time, we will get to the transformer networks, to GPT, to BERT, to whatever they are called. As usual, you will find more information in the description. I hope you like this video. I hope you subscribe to this channel. I hope you give it a thumbs up. I hope you watch it. Oh yeah, you already watched it all the way to the end. I hope I will see you soon. So thank you for watching. See you soon. Thank you and bye.